In the previous video, we talked about how electrons interact with the resist material and how different process choices impact the resist sensitivity. In this video, we will start off by discussing how hardware choices impact your right. We've seen how certain choices that we make with our process will influence the resist sensitivity. Here, I want to emphasize how most of those processing choices don't have a ton to do with the actual EBL hardware. For a given accelerating voltage, the resist sensitivity is independent of other EBL hardware choices, and it is a value that you can determine experimentally. Your choice of photoresist, your choice of developer, even your substrate determines your resist sensitivity. But once you find that number, it is a known quantity. On some EBL tools, the software will let you specify that resist sensitivity and automatically adjust tool settings to give you the desired dose. But that isn't how our Crestec tools are set up. On a Crestec tool, you specify the length of time that you want to dwell at a given exposed shot. That means we need to do some calculations to convert from a resist sensitivity to an exposure time, and that exposure time is going to depend on some hardware and software choices that we are now going to make. So, what hardware options do we have? The field size and number of dots per field determines the shot size. The beam current determines how many electrons will be hitting the resist, and the dwell time, or dose time, is how long the beam rests at each individual shot. We will talk about how each choice impacts your right. The equation that we have to balance is shown on the right. Here, I have solved for dose time, but you can rearrange this equation as needed. Sensitivity is that constant, experimentally determined number that we've been discussing, and it has units of microcoulombs per centimeter squared. That area dependence is important. This is why the field size and number of dots is in the equation. The area of each shot will determine how long the beam must dwell on that shot. Bigger shots need longer dwell times. The beam current also makes sense here. The number of electrons incident on the sample will also determine how long we must dwell on each individual shot. So knowing that this is the equation that we need to balance, let's see the impact of different choices on the patterns that we are trying to expose. The main consideration when thinking about beam current is that the diameter of the electron beam will depend on the current. Since electrons repel each other, a larger beam current will result in a larger beam diameter. The manufacturer has provided estimates for the beam diameter at beam currents ranging from 100 picoamps to 100 nanoamps for both the Crestec 130 kV tool at 100 kilovolts and the Crestec tool at 50 kilovolts. For the 100 kV tool, we can see that there is only marginal improvement in beam diameter below 1 nanoamp, and on both systems, the beam diameter bottoms out at about 2 nanometers at very low beam currents. We also see that the beam diameter is significantly smaller at all beam currents for the 100 kV system, which is the expected behavior since it's at a higher voltage. So what does this mean for you? Well, it means that you won't see a significant benefit in resolution of your features by writing with a beam current below 1 nanoamp. There might be other reasons you want to choose a lower beam current, as we shall see, but resolution won't be one of them. The last thing I will mention is the range of beam currents we can achieve on the two systems. On the Crestec system, the 50 kV system, currents can range from 25 picoamps up to 7 nanoamps. On the Crestec 130 kV system, currents can range from 50 picoamps up to 100 nanoamps. But note that if you need beam currents in excess of 20 nanoamps, you need to reach out to the process staff, as this does require some staff level setup to achieve. Returning to our balance equation, the next pieces that we will consider are how the choice of field size and the number of dots per field impact your right. There are 5 options for field size and there are 4 options for the number of dots per field. You can mix and match all possible field sizes and all possible dot settings. For instance, a common choice is a 300 micron field size with 60,000 dots, which gives you a 5 nanometer shot size. Or you could use a 600 micron right field and 60,000 dots, which will give you a 10 nanometer shot size. Or you can use a 600 micron right field with only 10,000 dots, which gives you a 60 nanometer shot size. We will see examples with each of these choices in a moment. Please consult with process staff before using either the 1200 micron right field or the 240,000 dot option, as there is additional information needed to properly use these settings that I am not covering in this video. So, how do you decide which shot size settings are appropriate for you? Let's say that we've chosen a 300 micron field size with 20,000 dots. That means that every shot is 15 nanometers in size. If we're trying to write an 80 nanometer feature, this means that we have 5.33 shots per feature. The tool will only expose integer numbers of shots, so you won't be exposing an 80 nanometer feature, but a 75 nanometer feature. This might be perfectly fine. After all, you might want to be undersizing and overdosing, as we discussed in video 1, but you should be aware that this is happening. In general, your shot size should be an integer divisor of any critical feature sizes. Larger shot sizes will typically mean that you have faster throughput, although you have to be careful to avoid higher line edge roughness. To understand this, let's look at an example design. This is just a design I made up to illustrate some of the issues you may encounter. The colors are to make it easier to identify different parts of the design. We have the blue inner circle and leads, the red middle arc, and the yellow outer arc. The diameter of the blue inner circle is 200 nanometers. The outer diameter of the yellow outer arc is 600 nanometers. So these features are small, but they aren't absurdly small. Now, let's see what happens when we work with different shot sizes. On the left, we have the result when we use a shot size of 60 nanometers. The yellow outer arc is grossly misshapen, and the red middle arc is not very circular. The blue inner circle looks acceptable, but the blue leads are also incorrectly shaped. Now, this is an exaggerated example. If you saw this during your data prep, you wouldn't proceed. But the 10 nanometer shot size also has some of these discrepancies. The blue leads are a little misshapen, and you can see some roughness on the edges of the red middle arc. In this example, the 5 nanometer shot size gives the closest approximation to the original design. Does this mean that you always want to use the smallest shot size you can? Maybe, but there are some costs to choosing smaller and smaller shot sizes. Let's look at what we needed to do to get a 5 nanometer shot size. We needed to use a 300 micron right field instead of a 600 micron right field. Larger field sizes means that you'll have fewer stitching errors in your pattern. A stitching error is when there is a discrepancy between shapes at the edge of a field. And because the stage has to settle after every move, you have less stage settling time with a larger field as well. If shot size is not a limiting factor, you will generally want to use the largest field size available to you. Another cost of using a small shot size has to do with the ability of the tool to accurately time each individual shot. On our Crestec tools, the units we use for dose time are microseconds, but we are routinely talking about fractions of a microsecond. The theoretical minimum dwell time on either of our Crestec tools is 0.1 microseconds, or 100 nanoseconds, which provides a bit of perspective of how fast these exposures are occurring. The practical minimum dwell time is quite a bit higher than this. I typically recommend dwell times at 0.3 microseconds and above. When members have tried to write faster than this, we've seen some discrepancies due to hardware failing at these high speeds. If running at these high speeds is critical for your work, please reach out for an in-depth conversation. For the purposes of this video, the main takeaway is this. It is possible to choose a shot size that is too small for the timing circuitry. For a given beam current, smaller shots need a shorter time, and since there is a limit on how fast we can write, that can limit what shot size we can choose for our pattern. There also happens to be an upper bound on how long you can dwell at any particular dot, but we run into this limitation far less frequently than we run into the minimum dwell time boundary. What this means in practice is that we commonly solve the balance equation not for dose time, but rather for beam current. We routinely run the tool at the minimum dwell time, and since we saw that resolution is not strongly dependent on beam current, it is often the case that we can use whatever beam current works to balance the equation. This brings us to the final piece we need to consider when choosing field size, dots, and beam current, which is the total exposure time we can afford. What does this look like in practice? Well, let's look at our example pattern again and consider our 3 different shot sizes. In order to make this a more relevant example, I have arrayed each individual element to form a larger pattern. In case A, we're using the overly large 60 nanometer shot size. To run at the chosen dose time of 400 nanoseconds, this will require a beam current of 27 nanoamps. On the high side, but probably doable, and the estimated write time will be just shy of 14 minutes. Now, we can all agree that the pattern fidelity at this shot size is poor, but even so, this gives us a sense of just how long it will take to write this pattern. Moving to case B, where the shot size is 10 nanometers, we now need a beam current of only 750 picoamps with the same dose time, and the write time has increased to over an hour. And in case C, with a 5 nanometer shot size, the beam current drops down to 187 picoamps, and the writing time is over 2 hours. The increase in writing time makes sense since the dwell time for every shot is the same, and there will be more exposed shots at a 5 nanometer size than at 10 nanometers or 60 nanometers. Now we can see the true cost of fidelity, total write time. Now, 2 hours is not an unreasonably long time to be using a piece of equipment, but the total extent of this pattern is only 200 microns by 200 microns. If you need to write a pattern across an entire chip, or worse, an entire wafer, this becomes impossible, and compromises in pattern fidelity will be required. Throughout this video, I have referred to our balance equation, and that is where we will end this particular tutorial. I hope you understand that this is truly a matter of balance, and what your priorities are will determine the best choice of parameters for your exposure conditions. The next video is where we will start discussing actual tool operation.